Good afternoon. Welcome to the Chemistry Department IITMadras webinar series. And I would like to welcome all of you and thank you for your presence as well as for the participation that you will have. And it's also my great pleasure to introduce you, our speaker, who is of course well known to all of you. However, I would still do a formal introduction as is, it's always preferable to do in a meeting of this sort when there are large number of others who are also joining for the first time and whom we should introduce the speaker on all the achievements and the accomplishments that he has had in the last many years of his academic career. So it is a great pleasure for me to introduce Professor Chandrakumar. He has sent me a very brief note. I would like to say much more than that, but due to the paucity of time and also keeping this reasonably short, let me go with what he has given. He has done his early schooling in Tiruchirappalli in Campion School, and later did his bachelor's in chemistry in Loyola College in the University of Madras. And he is our alumnus, IITMadras alumnus. He did his master's in the IIT Madras and continued to do a PhD and completed it from IIT Kanpur. He has been a research associate in the beginning, right after his PhD or soon after that, in the CSIR, Central Leather Research Institute in Chennai, where he grew up and also where he moved up the the establishment from the level of scientist C when he joined through to scientist G, which is at the very senior level. He joined IIT Madras around 2001. I'm in 2000 or 2001. I'm not sure of the year, but
2001.
2001. And he joined as a professor in 2001 and has been the professor of Professor HAG, the current the senior chair position. And he is also the Institute Chair Professor of IIT Madras, in addition to being Professor Emeritus in IIT Chennai currently. So he is also the founder of the Magnetic Resonance Research to the CLRI CSIR lab. And in IIT Madras, he has established the MRI and the MRS Center. So these are his academic activities, and he has received numerous awards. Before that, I would also tell you his major research interests are in magnetic resonance spectroscopy and imaging, and has had, of course, numerous publications in all the top international journals and numerous international patents as well, and has also co-authored the monographs and edited journal special issues. In fact, I came to know of his book co-authored with Professor Sankaran Subramanian while I was still in McGill University being a student of Professor Brian Sanctuary, who is an NMR theorist and who published a lot of theory papers in the early days of in his earlier career. So I knew from that point onwards that there is a very, very strong theoretical and experimental NMR individual whom I would have the pleasure to meet. And I think I met you first time in 1995 in CLRI.
That's
when I was
right.
trying to
That's
return
right.
to India. The next year, of course, I came back to IIT Madras. It was a pleasure meeting you and knowing you and talking to you.
My pleasure all the way.
Professor Chandrakumar has a very large number of awards. I have to read only a few select ones. He was a Max Planck Fellow, MPI BPC in Göttingen, and he was later visiting scientist at the Universitat.
Oh, this is DFG, Deutsche Forschungsgesellschaft?
Gesamthochschule Siegen, isn't it?
Gesamthochschule Siegen.
Hochschule Siegen, okay.
Yeah.
And then he was a DFG guest professor in the Universitat Ulm.
Yeah.
Visiting professor in the Universitat Joseph Fourier in Grenoble in France, and also visiting professor in the University of Osaka in Japan. He received CSIR Young Scientist Award of Chemical Sciences very early in the career, and soon became the Fellow of the Indian Academy of Sciences, and received the S.S. Bhattnagar Prize for Chemical Sciences while he was in CLRI. I remember attending that function.
Absolutely.
By that time, I had already joined IIT Madras, and I met him at that point of time also.
Yes,
and soon he became the Fellow of Indian National Science Academy. and has received the Millennium Medal from the Indian Science Congress. Has also received the Professor Asundi Memorial Lecture, has given the Asundi Memorial Lecture Award in INSA, and the recipient of the Rangadama Rao Memorial Lecture Award, also INSA, and CRSI Silver Medal, and currently also the JC Bose Fellowship. So it is a great pleasure to have you tell us about the discovery of the spin, or rather the COVERY of spin and after, as you said. And this lecture, in his own summary, traces the strange and the nuanced history of spin and the subsequent blossoming of spin resonance spectroscopy and imaging, otherwise known simply as magnetic resonance, as among the foremost techniques to characterize molecular structure, dynamics, distribution, and transport, besides serving as a model system for ensemble quantum computing. Several applications of magnetic resonance spectroscopy and imaging are included from his own field of research. Professor Chandrakumar, over to you.
Well, thank you very much, Professor Mangalasundar. I want to congratulate you on structuring this whole series of webinars. It's a brilliant idea. And I know that it also takes a lot of effort on your part to keep this going and bring in a number of talks of very wide general relevance in addition to specialist seminars as well. So hats off to you.
Thank you.
And ladies and gentlemen, all of you who have decided to join in this evening, a warm welcome to you in these COVID times. I hope COVID-19 will be long past part of our memory, and we will all live to tell the tale to our grandchildren in the coming years. Now, let me start the seminar without further ado. The story starts almost 100 years to this day, about 1920. And there was this notion floating around from Bohr and Sommerfeld and others, which they called the space quantization. What they meant by this was that because of the restriction and the possible values of the z component of angular momentum, where z is an externally defined but otherwise arbitrary direction, along which you might choose to impose, for example, a magnetic field, or if it's a Stark effect, an electric field, some reference direction called z. So they found that there is a restriction on the possible values of the z component of angular momentum. And this, of course, automatically means that the angular momentum vector can have only certain orientations in space. And this was termed as space quantization. Now, the strange thing about this, dear audience, is that the very theory people who had forwarded this proposal and made this name or this nomenclature actually did not believe that this was any physical reality. They just said, it's just something in our thought, in our mind. There's something we call the space quantization, because the z component of angular momentum can have only discrete values, and therefore the angular momentum vector can have only certain discrete orientations in space. But this is not a physical effect. But then they did not reckon with Otto Stern. Now, Otto Stern, for chemists, you will remember, is also named, the Stern-Volmer equation. This is the same Stern that is the villain of the current piece of Discovery of Spin, okay? The villain or the hero of the piece, as you may wish to call him one way or the other. This is the same Stern who did the Stern-Volmer equation as well, okay? Now, this guy, I've heard some ads in the past several years when there used to be a popular TV brand which was supposed to be the neighbor's envy and the owner's joy or owner's pride. Now, Otto Stern was probably the theoretician's nightmare, but then equally or even more so, he was the experimentalist's nightmare as well, as we shall see. So Otto Stern said, okay, if there is space quantization, let me try to prove it. Of course, he was a skeptic. He was a skeptic. He said, okay, let me set about the task of proving it. And later on, this is what John C. Slater had to say in his book in volume 1 of the Quantum Theory of Atomic Structure, that Stern and Gerlach in the early 20s, between 1920 and 22, wished to demonstrate the space quantization of atoms experimentally. They produced a beam of atoms of silver vapor by evaporating them from an oven at about 1,000 degrees Celsius and suitably collimating the beam of relatively slow atoms. They then passed these atoms through a transverse magnetic field. What you mean by transverse is that the direction of propagation of the beam and the magnetic field were perpendicular to each other. That's what we imply by transverse magnetic field here. It is transverse to the motion of the beam of atoms, which would then be expected to space quantize the angular momenta, also transverse to the direction of motion, and then pass it through a transverse inhomogeneous magnetic field in the same direction, in the same perpendicular direction to the direction of motion. Not the third mutually orthogonal direction, but the same old direction as the field itself. The inhomogeneous segment of the field would also be in the same direction. This would then exert a transverse force on each atom. And atoms which have been space quantized in the homogeneous field will now sense forces in opposite directions in the inhomogeneous field. And then they actually found that there are two beams into which the single beam of silver atoms was split. The input was a single beam of silver atoms at about 10 to the minus 5 millibar coming out from an oven at about 1,000 degrees. And there was this magnetic field. The inhomogeneous part was about 3.5 centimeters long with a magnetic field strength of about 0.1 Tesla and a magnetic field gradient of about 10 Tesla per centimeter. So huge gradient. We'll see towards the end of the seminar that has been exceeded today, but we are talking about 1920 to 22. Okay, and they found that they got two beams from a single input beam. They got two at the output, which could be detected separately. Now a little bit of the history. So when Stern tried to do this experiment, he enlisted the support of the experimentalist Walter Gerlach. Gerlach was already interested in beam experiments. Beam experiments had been discovered around 1911 or invented in 1911 by Dunoyer in France. And Gerlach wanted to check the diamagnetic behavior of single bismuth atoms as opposed to a bismuth crystal. And he was therefore fashioning and designing a very highly inhomogeneous magnetic field. And this is where Stern walks in and they decide to join hands. Gerlach has this highly inhomogeneous magnetic field, and Stern wants to check what happens to a beam of silver atoms in this highly inhomogeneous magnetic field. Now, Max Born was in the same university in Frankfurt when Gerlach was there, and Max Born said, this experiment will not work. Even the Gerlach experiment, leave alone the Stern part of the story. But then Gerlach quoted a Zurich physicist called Edgar Meyer, who had said in German, "Kein Versuch ist so dumm, dass man ihn nicht probieren sollte." Translated into English, it says, no experiment is so dumb that it should not be tried. And that is how Gerlach persisted with his notion of a molecular beam, and soon he joined hands with Otto Stern. Now, what shall we say about Otto Stern? As I said, one could view him as the nightmare of theoreticians as well as being the nightmare of experimentalists. He is one of those guys who straddled the worlds of theory and experiments, it looks like. Some people called him an experimenting theorist. Other people said he's not a theorist by training. But be that as it may, this proposal of Otto Stern to look at the purported space quantization of silver atoms in a highly inhomogeneous magnetic field, despite his careful design of the experiment, okay, he and Gerlach took the better part of a year to actually accomplish it. Okay, and once again, Max Born was there to dissuade them. He had said, I tried to persuade Stern, there was no sense, but then he told me that it was worth a try anyway. Because please remember, the theoreticians who had coined the term space quantization apparently did not believe in it as a physical reality to begin with. Okay, Anyway, the beam method first employed by Louis Dunoyer in 1911, that's what Stern and Gerlach used. And the actual parameters that the Stern Gerlach, actually the paper is by Gerlach and Stern, okay, in Zeitschrift für Physik 1921 and 22. And we'll see the references. Actual parameters were 10 to the minus 5 millibar. The length of the inhomogeneous magnetic field was 3.5 centimeters. The magnetic field intensity was about 0.1 Tesla, which is 1,000 Gauss. And the gradient was 10 Tesla per centimeter, which sounds absolutely heroic. And they got a princely splitting of the single incident beam at the output. It was split into two. And the splitting in the direction of the magnetic field Z was all of 0.22 millimeters. 0.22 millimeters, ladies and gentlemen, which means that if their experimental setup had been misaligned by 0.01 millimeter, that's it. The experiment is all berserk. Okay, so 0.01 millimeter of precision was required in aligning all this, and they saw this, splitting of one beam into two, and the separation of 0.22 millimeter, and space quantization had been experimentally proven. What's happening in the experiment? The potential energy of the magnetic moment of the silver atom in the magnetic field is V is equal to minus mu dot B. And since the field is in the Z direction, you find immediately that the force in the Z direction is the negative of the Z derivative of the potential energy. So that is mu Z into delta B by delta Z. And when they measured it and found the splitting of 0.22 millimeter, they were able to infer that this corresponded to mu Z of either plus the Bohr magneton mu B or minus mu B. That's it. They got exactly the value of the Bohr magneton plus or minus EH cross by 2ME. The expectation based on classical physics is that due to the random thermal effects in the oven from which the silver atoms were shot out, the magnetic dipole moment vectors of the atoms should be randomly oriented in space. So there should be a continuous spread in the Z component of the magnetic moment of the silver atoms, all the way from minus mu Z to plus mu Z. A line then should appear on the observation screen along the Z direction. Instead, what was found was that the silver atoms just arrived at the screen at two spots or 2 points that corresponded to the magnetic moment, so plus or minus mu B. So what was the interpretation? The interpretation was this proved the space quantization. The silver atom was then thought to be in the p state with the orbital angular momentum quantum number, which was the only type of angular momentum known up to then of 1 unit quantum number, split into two beams with the Z component ML of plus minus 1. And magically, it was imagined that somehow the third ML value, the beam with the component ML value of 0 was unobservable. So that's really strange in thinking back now today, right? In hindsight, we are all extremely wise, but this was the interpretation of the Stern-Gerlach experiment. Space quantization was proven, but it was all about the p state of a silver atom, which should have been split into three beams. But since the ML is equal to 0 component of the orbital angular momentum would not be observed in the magnetic field, you got two beams, period. And the splitting and the inferred magnetic moment was just right, plus or minus the Bohr magneton. That's what you expect from the ML value of plus or minus 1. So everything seemed to fit perfectly. Now, this came up, was actually originally published in 1921 and 22 by Stern first, the experimental setup, and by Gerlach and Stern, the actual experiment and their findings in 3 papers in a series in 1922. So 1921 and 1922 is when this work saw the light of day. 1925, Goudsmit enters the picture. He had worked in Paschen's lab and tried to understand the Zeeman effect in the hydrogen atom spectrum and the anomalous Zeeman effect. And he found that the Zeeman effect was easy enough to understand in terms of the orbital angular momentum, but unless by 1925 he came to the conclusion with his colleague Uhlenbeck that unless they postulated a half odd integer strange quantum number, intrinsic angular momentum, which is a half odd integer, unless they postulated that, they could not explain the anomalous Zeeman effect. So Gaudsmit says one of the first results that came out was a new interpretation of the spectrum of the hydrogen atom, anomalous Zeeman effect. We had Sommerfeld's hydrogen spectrum, and for formal reasons, and because I had investigated all those things, says Gaudsmit, we obtained a new interpretation of the hydrogen spectrum, the new term scheme. And the curious thing is that because I knew all these intensity rules and so forth from my visit to Pashan's lab, I had already guessed the correct formulae. That was my contribution. I knew which formulae one had to take. One took the classical expressions, and instead of integer quantum numbers, one put in half integer quantum numbers, did a few other things. It was like magic, but it precisely fitted. And what I found so delightful, if you believed it, was then the so-called forbidden transitions due to the anomalous Zeeman effect, which Pashan had seen, was not forbidden at all, but was a real spectral line which should be present. And that was, of course, a matter of source of great delight. Then when they wanted to publish this work, Ehrenfest apparently told Gaudsmit, well, that's a nice idea, though it may be wrong, but you don't have a reputation, do you? So you have nothing to lose. So they went ahead and published. Now, the strange thing, ladies and gentlemen, is this bunch of publications was fully 3+ years after the Stern and Gerlach-Stern papers. And these two bunches of papers were not connected in the community for another couple of years. In fact, as we understood after 1927, when R.G.J. Fraser seems to have pointed it out, the Stern-Gerlach experiments actually demonstrates electron spin. It is space quantization, but it is not the space quantization of a p state with a magical disappearance of the ML is equal to 0 component. It's nothing like that. And it is a spin half, and you get two beams. And they have the Z component of plus minus mu b, the Bohr magneton, because the G factor is 2. The spin quantum number is half, but the G factor is 2. And so that was what was happening in the Stern-Gerlach experiment. So the puzzle remains that although it was all published by Stern and Gerlach in 1921 and 22, and then Gaudsmit's hypothesis of spin half with Uhlenbeck in 1925 to understand the hydrogen spectrum and the anomalous Zeeman effect, nevertheless, nobody connected these two kinds of work until Fraser came along and said, yeah, this is the same thing. That Stern-Gerlach effect is really the spin. 1927 was when he noted it. So if you look at a schematic diagram of what is happening, the oven producing the beam of silver atoms is here. Then it goes through this magnetic field. You see one pole is really pointed and the other one is kind of scooped out. And therefore, you have a huge gradient in this direction, the vertical direction, which in the coordinate system is Z. Here we have shown the axis of direction of propagation of the beam as Y. And then you see you get two spots or two extended lines. It is separated in the Z direction. And now we can say one of them is a spin up with the SZ component of plus h cross by 2. The other one is a spin down with the SZ of minus h cross by 2. Now, Stern and Gerlach had therefore found electron spin without noticing it. And as people said in much later years into the 21st century, this was the right experiment with the wrong theory. All right. Stern, however, was not one to give up so fast. So he probably missed the Nobel for having covered the electron spin rather than discovering it. Okay. He had actually discovered it, but it was just misunderstood by everybody, including himself. But he was not to be put off, and he continued his work with nuclear magnetic moments. And this is far more heroic because here you have a far weaker magnetic moment. So he worked with orthohydrogen and he wanted to measure the magnetic moment of the protons. and his friends, his good friends, the theoreticians, were back at work with him. They chided him for having decided to undertake this experiment, because they thought, they already knew that the magnetic moment of the proton is just plus the nuclear magneton, plus mu n. Not the Bohr magneton, of course. It will be scaled by the nuclear mass, but it should be just the plus nuclear magneton. Of course, the magnetic moment is always plus, so I don't have to say plus. It's just the nuclear magneton. So they saw Otto was a nut, okay, trying to measure this. Lo and behold, what did Otto Stern find? He found that the magnetic moment of the proton, which he measured by using orthohydrogen, which of course has two uh, parallel proton spins, turned out to be somewhere around 2.5 times larger than the predicted value of the nuclear magneton. And this he published in 1933. To this day, it's a matter of debate whether the theoreticians have been able to properly come up with the correct number and the correct value in respect of the magnetic moment of the proton. You see, I've just given two references here in quick succession. One which says a calculation of nuclear and magnetic moments from first principles is not yet available. Another, around the same time, says nuclear and magnetic moments have been successfully computed from first principles, requiring significant computing resources. I would say, do the experiment. You have the best possible measure of the proton magnetic moment and any other magnetic moment you might ever care to get. So let's just move on. Therefore, just a few more words about Stern, the experimenter. Stern was supposed to be rather clumsy with his hands. And in fact, Max Born says he was about as clumsy with his hands as I was with mine. So he felt that they were kindred spirits, right? Max Born and Otto Stern. But then, not only was he clumsy with his hands, Otto Stern insisted in invariably smoking a cigar, which therefore, apparently, when it was not in his mouth, one of his hands would be occupied holding the cigar. And in fact, there is a story which I don't quite believe, because the first pass, Gerlach found the two beams, but in the second pass, when Otto Stern was with Gerlach, they failed to see the two beams. And the story now goes, but this was not the initial observation in my understanding. This was the second observation by the same workers. He smoked a cigar. This was a cheap cigar. It had a high sulfur content. And when he blew the cigar smoke onto the flange where the silver atoms had deposited, silver sulfide was formed, and only then they could see the deposited silver. Had he not blown a bad cigar with high sulfur content onto the flange on which the silver atoms had deposited, the joke goes, you might have missed spin all over again. Okay? Anyway, so he had this. Although you might say he was clumsy, never did an experiment with his own hands, and if something was falling, he would not even attempt to catch it, and so on. But he was also the experimentalist's nightmare, because he would just have it exactly so. He would make calculations, and he would not tolerate more than a 5 or 10% deviation of the observation from the calculation, because if the deviation is more than 30%, something is drastically wrong. So he's very demanding on his experimental collaborator, okay, and also very demanding in terms of the understanding he required of his theoretical friends. Okay, so he taught a way of experimenting. This is what Frisch had said in the previous slide, but Segre later said he taught a way of experimenting that I had never seen before. He calculated everything possible about his apparatus, such as the shape and the intensity of the molecular beams that he expected to generate, and did not proceed until preliminary experiments were in complete quantitative agreement with his calculations. This modus operandi slowed down the preliminary work. No wonder it took a year, huh? But it shortened the total time by making it possible to avoid errors, and was absolutely essential for the extremely difficult experiments that Stern was conducting in his lab. The method allowed him to localize sources of misbehavior in the apparatus and of failures, and to come to a firm decision as to what was new and what was unexpected and what was just errors. New and unexpected had to be reproducible, of course. And this was a rigorous and useful method of schooling. But also, as a rule, these experiments that they were doing in Stern's lab were so difficult that nobody else in the world was attempting them. So one could imagine a lot of tension and pressure in the group, but the fact that there was no competition created an oddly relaxed atmosphere, according to Frisch. All right, that will do with the history. So what is spin? It is considered to be an intrinsic angular momentum. It is not really connected to the physical rotation of the particle because of the infinitesimal radius, less than 10 to the minus 17 meters for an electron. The angular velocity would need to be infinitely large. So it is not physically connected to the rotation of the particle. Some workers believe that the electron spin is a consequence of Zitterbewegung. Now, don't ask me what about the nuclear spin. I'm not the one to answer you. The next question is spin a quantum mechanical effect or is it a relativistic quantum mechanical effect? Normally, it is held that you need to get to the Dirac equation, which is relativistic quantum mechanics, to see spin. However, practitioners of geometric algebra, starting with David Hastings, who founded this after Clifford and, after the quaternions had come and gone, Clifford had come and gone as well. And then David Hastings reinvented this and he expanded this into a whole field called geometric algebra. They believe the Dirac equation is not required to explain spin because as soon as you look at the time-dependent Schrodinger equation, you have the unit imaginary there. IH cross d psi by dt is the Hamiltonian's times psi. And the unit imaginary is the quaternion. And there you have the seed for the fact that if you square the unit imaginary, you get -1. And you need to take the unit imaginary to the 4th power to get back to +1, the identity. And that's exactly what the topology of space, if you take the spin function, you need to make 2 circuits to come back to the initial state. If you make 1 circuit, you get the negative of the initial state. That's what a spinor wave function is all about. So it may be deemed to arise from the quaternion behavior of the unit imaginary, which is already found in the Schrodinger equation. But then, lo and behold, the Möbius strip, which our kids can make as they tear their paper up, you just have got them to introduce a twist in the middle and paste up the ends. You have a spinor right there. Because if you take make a trajectory, visit with your pencil, tracing a trajectory, you start on the top of the strip and then you end up on the bottom of the strip at the end of 1 circuit. Complete the 2nd circuit, then you're back at the top of the strip. That's because you've introduced this twist in the Möbius strip. Now, Möbius strip is well beloved of chemists as well. But then this is, you may call it the quaternion, you may call it the spin half behavior. As far as the topology of spin space is concerned, the Möbius strip, which is a completely classical object, already exhibits the spinor behavior. So you can make of spin what you will. But then the next great advance was made within years of Stern and Gerlach's experiment, within about 10, 12 years, by Rabai, who showed that electromagnetic radiation polarized transfers to B naught is able to flip the spin states from the upspin to the downspin state and vice versa, provided the radiation frequency matches the Lama frequency of the spins, the precession frequency of the spins, and provided the radiation is transfers to the magnetic field. The radiation magnetic field component should be transfers to the main Zeeman magnetic field component, magnetic field. Please remember, in the Stern-Gerlach experiment, you have the precession and you have the effect of the force. They were worrying about the force alone to get the beams to split. But what Rabai did was introduce the next clever trick, exploited the precession and made it much easier to detect the resonance by getting the diffuse beam. You know, they could not really separate them into 2 beams because they said the magnetic moment of the nucleus is so tiny. And therefore, more often than not, except for the special cases such as orthohydrogen and so on, you will just find one beam becoming diffuse as it passes through the inhomogeneous magnetic field. And so they found a way of refocusing it by getting these spins to undergo transitions, flipping the spin state by resonant radiation. That was Rabai's contribution. So, but please note, spectroscopic or resonance method measures differences of eigenvalues, whereas the Stern-Gerlach experiment actually measures the spin eigenvalues, plus half set component or the minus half. It is not the difference of plus or minus 1 unit. Okay, that is another unique thing about the Stern-Gerlach experiment. You are measuring the eigenvalue. In any spectroscopic or resonance experiment, you are not able to measure the eigenvalue. You're only able to measure the difference between a pair of eigenvalues. Okay, once this resonance started, the game really started blossoming in bulk matter within a decade after Rabi's molecular beam resonance experiments. Zavoysky came up with ESR or EPR in 1945. Purcell and Bloch came up with NMR in 1946. Dept and Kruger came up with NQR in 1951. When Bloch was asked what could be the use of this NMR, he is reputed to have said pretty little. And when Purcell was asked what could be the use of NMR, he is reputed to have said, well, maybe it can be used to measure a magnetic field. And there is a further story that Purcell has recorded in an American Journal of Physics article of his reminiscences, that when the chemistry research manager of DuPont sought and got an appointment with Purcell to discuss the possible chemical applications of nuclear magnetic resonance, a week later, the appointment was fixed and they had their chat over a cup of coffee or whatever. And Purcell found himself making a strong case that NMR could have absolutely no possible consequence for chemistry whatsoever. Okay, so much for even the founding fathers. We all very wise in hindsight, of course. Okay, but we would have never had many of us, most of us, not me certainly not me, would have had the foresight to think of a Stern-Gerlach experiment, to think of a resonance a la Rabi, or to think of what Purcell and Bloch and Zavoysky and Dept and Kruger did. But the properties of spins are they're ideal 2i plus 1 state systems where I is the spin quantum number. This is not the unit imaginary little I. This is the capital I, the spin quantum number. It's an excellent illustration of the quantum world. And it's only very weak coupling that spins exhibit to the macroscopic world. And in the case of nuclear spins, it is extraordinarily weak. Electron spins are somewhat more tightly coupled to the outside world, but even then, that's not very strong in paramagnetic substances or in free radicals. But nuclear spins, they just don't talk to anyone in the macroscopic world, more or less, for longish periods of time. Therefore, you can have an excellent theoretical understanding and modeling, infinite maneuverability with all the advances in radio frequency and microwave technology, much of which was thanks to the Second World War radar technology. And long-lived macroscopic coherences or superpositions of the plus half and minus half states could be produced by suitable radio frequency or microwave excitation. And measurements in magnetic resonance are done, they're like ideal measurement. They're not projective measurements at all. You don't project a superposition state into one of the eigenstates when you do a magnetic resonance measurement, unlike most other measurements on quantum systems. Most other measurements on quantum systems are projective measurements. You have a superposition state, you try to measure it, it collapses to one of the eigenstates. The fun part with magnetic resonance is you measure it without hardly any perturbation of the state. So a superposition state will persist for as long as irreversible effects of decohering takes place, which is called relaxation. So the applicability ranges all the way from, because these are measurements with negligible perturbations, right? So the applicability ranges to everything under the sun, more or less, except for bulk metals. Even dispersed metals are game, but bulk metals, because of the skin effect, right? Skin effect, not the spin effect, the skin effect, radio frequency cannot penetrate, and therefore bulk metal investigations by NMR, not really a go. Okay, but the applicability otherwise ranges from molecules and materials to living matter, medicine, and man. Here is Otto Stern, the nightmare of theoreticians as well as the nightmare of experimentalists alike, finally got his Nobel Prize in 1943. Here was his collaborator, Walter Gerlach, Uhlenbeck and Goudsmit, who had hit upon the formula that the anomalous Zeeman effect would no longer be anomalous once you posited a half-integer quantum number, and Uhlenbeck recognized that this is a new quantum number and a new angular momentum, but all by just fitting experimental atomic spectra. No experiments on their part, not connecting with Stern-Gerlach either. Okay. Then comes Rabai, 1 year after Stern. Rabai had himself postdoc with Otto Stern and learned the molecular beam method in Germany with Otto Stern. But later on, Stern migrated to the US and Rabai did also. And I believe the 1943 and the 1944 Nobel Prizes for Physics were both handed, because it's the Second World War time maybe, handed to the respective prize winners, Stern and Rabai, in the United States, because they were both working in individually in different laboratories, different universities, by that time, both of them in the US. Okay? Then come Bloch and Purcell, 1952 Nobel in Physics, and then 12 years saw 4 Nobel laureates in magnetic resonance between 91 and 2003. Our great distinguished Richard Ernst, an Indophile, whom many of us are privileged to know, Nobel Prize in Chemistry in 1991. The same magnetic resonance at NMR, which Bloch and Purcell had predicted would be worth pretty little, or maybe could be used for measuring magnetic fields, but certainly no use for chemistry. Richard Ernst showed how precious its usefulness was at his hands with all his new techniques of multidimensional NMR and so on, not to speak of Fourier imaging. Okay, so he got the Nobel in chemistry in 91. Here is this guy Osherov. He won the Nobel in 1996, not for NMR. When he was a PhD doctoral student somewhere around 1972 in the US, he did the experiments that documented the phase transitions in helium-3. And how did he measure these phase transitions? By none other than NMR. So from that day to now, whenever Osherov gives a popular lecture or even a learned lecture, he never fails to mention just how unexpectedly green the field of NMR has been. So simple sounding, almost trivial to the eyes of exalted people like Bloch and Purcell, but so precious in the final outcome. So he got his Nobel for the discovery of superfluidity as a doctoral student, together with his advisors, Lee and Richardson, superfluidity in helium-3. But he is a great, he sings paeans of praise of NMR, and Anthony Leggett, who won also the Physics Nobel several years later for his theory of superfluidity in liquid helium-3, had to see that his theory would mesh with the experimental NMR measurements of helium-3. So that is how wide the scope of NMR has been. At Kurt Wüthrich have the Nobel Prize in Chemistry 2002, taking it from small molecules like water or wax or drug molecules or small molecular species up to 5 kilodalton. It took it all the way to maybe 100 kilodalton or so, looking ultimately at the three-dimensional structure at the atomic level of chaperone proteins. In his case, he looked at a fragment of about 100 kilodalton in a 400 kilodalton protein, if I remember right. So he won half the Nobel in chemistry for NMR in 2002, and Paul Lauterbur on the left and Peter Mansfield on the right won the MRI Nobel in 2003. Now, Osherov thinks that there should be another NMR Nobel, and that should be for functional MRI, which was also discovered apparently in Bell Systems Lab by Ogawa. But functional MRI Nobel has not yet happened. Who knows? As long as Ogawa is alive, I guess there is a chance. Now, how do you measure spin? You could say you would measure it with with Stern-Gerlach experiment. Tough. So people were measuring it from the hyperfine structure in atomic spectra and from the intensity patterns in band spectra, and from Stern-Gerlach experiments on atoms in weak magnetic fields, where you would get 2j plus 1 into 2i plus 1 beams if j is the angular momentum of the atom, where I is the nuclear spin. Subsequently, of course, you can talk about being able to infer the spin quantum number by looking at the power versus flip angle ratio, and by looking at the intensity of NMR transitions and so on. But by far the most straightforward method would be Stern-Gerlach, except for the very weak effect, so, but it is possible in weak magnetic fields to measure it to the spin quantum number. Gamma is eminently measurable by NMR or EPR. There's no issue about that. Now again, to re-summarize as it were, the spin half is a two-level system. Any arbitrary spin with quantum number capital I are systems with finite number of energy levels whose energy is bounded both from the top and from the bottom. And because the energy is bounded from the top, please remember, what does a particle in a box look like in its energy levels? Yeah, there is a lower bound to its energy, but there is no upper bound, except for relativistic limits, you might say. Whether it's a 1D or a 2D box or a 3D box or a ring, or a harmonic oscillator or a rigid rotor or an electron in an atom or a molecule, it's always the same. There is no bound to the energy from the top. There is no upper bound to the energy. There's only a lower bound. And this gives rise to the thermodynamics that we are all so familiar with, that you cannot have negative absolute temperatures. But you can when you're dealing with spins, because spins have an upper bound to the energy. And therefore, the derivative of entropy with respect to energy can turn negative, and which means you have a negative absolute temperature. So spins have turned out, to be the ground of emergence of the possibility of negative absolute temperature. More recently, this has been taken beyond the spin degree of freedom to demonstrate negative absolute temperatures, even in translational degrees of freedom. But that's something for another day. Spins have turned out to be a marvelous testing ground, therefore, of quantum mechanics, also the archetypal quantum bit or qubit, and therefore quantum computing. Magnetic resonance spectroscopy in bulk phase delivers unique information on molecular structure and dynamics, leading, for example, to the understanding of direct protein interactions, to the structure of proteins in solution, as well as of materials in the solid state. Spatially resolved magnetic resonance delivers information in bulk phase on molecular self-diffusion in steady state without a temperature or a pressure gradient or any such gradient, just a magnetic field gradient. It can also deliver information and quantify flow. And also, in addition to those kinds of spatially resolved magnetic resonance, you have magnetic resonance imaging, which, for example, is so powerful and so highly sought after clinically because of its powerful soft tissue contrast capability. And then, of course, you might say the newest kid on the block is magnetic resonance force microscopy, and people have reached single electron detection with a 25 nanometer resolution at IBM research labs already by about 2000. So, magnetic resonance spectroscopy and imaging in bulk phase, only nuclei with spin greater than 0 can give you any NMR. It works in principle in gas phase, but it's a bit of a pain. But it's an absolute, works like a charm in liquids and solids, although for solids there can also be some challenges. Major application areas of NMR are elucidation of molecular structure, dynamics, distribution and transport, structural biology, materials, and clinical practice in biomedicine. Major application areas of electron paramagnetic resonance or electron spin resonance, valid only for species with unpaired electrons, works in liquid and solid states. Major application areas are oximetry, detection of free radicals, structure and bonding of paramagnetic species in general, transition metal complexes, rare earth complexes, and so on. Nuclear quadrupole resonance, only valid in the solid state for nuclei with spin greater than half, 1 or 3/2 or higher. Major application areas, explosives detection, and in general, lattice dynamics and solid state studies. But whatever you do in magnetic resonance, you will first destroy the spin order. If it's NQR, it is quadrupolar order. If it is NMR or ESR in a Zeeman field, you have Z magnetization, where Z is the direction of the Zeeman field. You cannot get a signal from the state of Zeeman order or quadrupolar order. You have to create a non-equilibrium state by the radio frequency pulse. And in the most common case, you will generate transverse magnetization, which is transverse to the longitudinal equilibrium state that you started with. And then you can detect it. And there's a small step from spectroscopy to imaging. It's a small step for Paul Lauterbach, but it's a giant step for mankind, as it were. If I were to mimic Neil Armstrong's phrase on the moon, spectra are obtained in highly homogeneous fields, unlike Stern-Gerlach experiments, where every part of the sample sees the same field intensity because the field is homogeneous, resulting in molecular information in the spectrum. Not in deflections and transport, but molecular information, chemical shifts, and coupling constants. Images are obtained also in homogeneous fields, but superimposed on these homogeneous fields, you have calibrated constant gradients, which result in a linear variation of the resonance frequency of any given species across the sample, where the precession frequency omega naught is now no longer just minus gamma b naught, but there's an additional term minus gamma g dot r, where r is the position vector of the molecule, which houses the spin, and g is the gradient vector. So that's the one small step to go from spectroscopy to imaging, but it's a giant step for mankind, right? The master equations of magnetic resonance. Now you will understand this. You've created a non-equilibrium state. Nothing on Earth likes being in a non-equilibrium state. So the spins, also being earthen creatures, will try to get back to equilibrium. And the master equations of magnetic resonance, first the classical master equation at the hands of Bloch phenomenologically, and then the semi-classical master equation originating in Redfield, Bloch, Wanksness, and Abraham for spins, treating the lattice classically, but the spins in a quantum mechanical treatment. These are the equations which give you the complete master protocol to understand what are happening to spin magnetizations in ESR or NMR or in principle NQR. Another major milestone was the production of echoes by Erwin Hahn. In 1950, he showed that inhomogeneous interactions can be refocused at his hands initially by a 90-degree pulse. So he gave a 90-degree pulse to produce the transverse magnetization and allowed it to dephase, and the FID gave you a decaying signal, and then magically, black magic, he rephased it by a 90-degree pulse, the second one, and then the FID built up again, produced an echo, and decayed again. So there is a non-equilibrium state, it decoheres and then recoheres, and you're back with the non-equilibrium state. Then important next steps came from Overhauser and Carver and Slichter to detect these magnetizations. Not only is the Stern-Gerlach experiment going to give you weak effects for nuclei, even the resonance method gives you weak effects for nuclei other than protons. And this is made possible in this day and age for arbitrary nuclei, anything in the periodic table, because of the methods developed by Overhauser, experimentally proven by Carver and Slichter. He proposed it for metal nuclei. You know, metals have a partially filled conduction band. There are unpaired electrons there. They will give rise to an ESR signal. If you saturate the electron spin resonance, he showed that the nuclear spin polarization would become a giant by a factor which is the ratio of the magnetogyric ratios of the electron and the nucleus. Later on, Hartmann and Hahn showed a more modest but a more routine method of getting improved sensitivity by transferring magnetization from high magnetogyric or high abundant spins to low gamma rare spins by making them resonant by matching the RF field amplitudes. Now, it's the Larmor precession frequencies in the Zeeman field are very different for two different nuclear isotopes like carbon and proton. But you give a radio frequency field with amplitudes in the ratio of 4:1 for carbon and proton respectively, then the nutation frequencies of the two nuclei become equal in the so-called rotating frame. And that was the magic that was wrought by Hartmann and Hahn. They demonstrated this both in the solid state and in the solution state. In phase transverse magnetization of abundant high gamma spins is thus transformed to in phase transverse magnetization of rare low gamma spins. And this probably marks the first coherent magnetization transfer experiment termed the rotating frame experiment. And when I started into this game, I never had a night's sleep since then. wanting to always do rotating frame experiments and yet more rotating frame experiments. But then the next major milestone was at the hands of Genet and Ernst and his group, Ernst et al., multidimensional NMR, where you prepare the spin system in a non-equilibrium state, let it encode the chemical shifts and couplings or spatial coordinates, and maybe you will transfer the magnetization, okay, in spectroscopic experiments, generally not in imaging experiments, but you might want to do it in imaging also, transfer it to coupled spins and then detect it. So you have now the encoding period, which is one virtual time dimension, and the detection period, which is a real time dimension. So you got two dimensions. So you can add more encoding and transfer steps before the final detection. So you could think of n-dimensional NMR. And this is one of the early spectra that came up from Bax and Freeman's group. It's a spectrum of 2,3-dibromopropionic acid, just a 90-degree pulse, a variable evolution time at a second 90-degree pulse, and then collect the FID, systematically repeat the experiment with incrementation of the evolution time. Look, the basic spectrum, because of equality of couplings of the M proton, which is marked in this figure, in the Newman projection, okay, it has equal couplings with the geminal partner and with the anti-vicinal partner. And therefore, it gives you an apparent triplet. The A and X is a nonlinear three-spin system. They give a doublet of doublets for the A and X and a triplet for the M. So the one-dimensional spectrum is bad enough. Basically, it has 12 transitions with 2 of them merging to give you 11 transitions. Look at the 2D. That's a real mess, right? But the important thing is these peaks on the diagonal give you nothing by way of additional information as compared to the normal NMR spectrum. But those multiplets off diagonal, they're the cross peaks. Every cross peak tells you that there is a coupling between 2 spins. Okay, a cross peak has 2 frequency coordinates, one in the evolution time and the second in the detection time. Diagonal peaks have the same frequency in both the evolution and detection times, whereas cross peaks have different frequencies in the evolution and detection times. This is a telltale proof that magnetization has been transferred from one spin in the evolution time to a coupled spin in the detection time. So all these cross-peak multiplets on either side of the diagonal are proof that in the dibromopropionic acid system, the A proton is coupled to M and X, the M proton is coupled to A and X, and the X proton is coupled to A and M. So you get 3 bunches of cross-peaks on either side of the diagonal. Okay. But our interest in magnetic resonance, just as for all researchers in all of spectroscopy, our main concerns are improvement of sensitivity and resolution. And our contributions have been, for the major part, to solution state studies. And of course, my hobby horse has been coherence transfer in the rotating frame. Hartmann and Hahn had shown it in the solid state, but also by J cross polarization in solution state. And we did what we called as isotropic mixing in solution state, as well as J cross polarization or planar mixing in solution state. And we elaborated this theme and got out a whole lot of new experiments and fairly good applications. Spectroscoping and imaging studies involving multiple quantum coherences, spin 1 NMR, like that of deuterium and lithium-6 in particular. Nitrogen 14 we have not addressed to a great extent. It's a much more difficult nucleus. We should be doing that, but you know, our group has always had a surfeit of manpower deficit. Okay, human resource deficit has been our hallmark all through my CSAR, CLRI years and subsequently here at IIT as well. So N14 we have not managed to get around to addressing. Other people have addressed it. It is more challenging. We would like to do that with our own methods. We haven't. But spin 1 NMR of lithium-6 and deuterium in solution state and in plastic crystalline solids, one-dimensional NQR exchange spectroscopy. Samannvita Pal had joined the audience. She is a professor at the IIT Jodhpur currently. I don't know whether she has already had to leave the group either because my presentation was too boring or as the dean there, she might have had to quit for professional reasons. But she was into this one-dimensional NQR exchange spectroscopy. We have been into a lot of optimal coherence transfer experiments. The initial ball was set rolling by V. Ramesh, and later on, it was, you know, it was really, Christy George went to town with this optimal coherence transfer experiments. microimaging and volume localized spectroscopy, Oberhauser dynamic nuclear polarization, and liquids and soft matter. And for microimaging and volume localized spectroscopy, Abhishek Banerjee and Christy George were major participants in the lab. And for Oberhauser dynamic nuclear polarization and liquids and soft matter, once again, Christy George, followed by Abhishek Banerjee and Arnab De. Some isotropic mixing experiments. Look at the spectrum of pyridine. If you look at the proton spectrum, you have 5 magnetically inequal protons. Imagine the forest of lines you will have. I have the spectrum somewhere, but we will not bother with it right now because of the paucity of time. But if you look at the per deuterated pyridine, you have just one chemical shift for the ortho, one line, and one each for the para and the meta. All the line widths are of the order of 1 hertz. The coupling constants are 115 millihertz, 181 millihertz, or 45 millihertz. There's no resolution because the line width is like 1 hertz. And we did a rotating frame isotropic mixing experiment, homonuclear. And we were able to show that we can do a 2-dimensional isotropic mixing or total correlation spectrum with completely unresolved couplings, so that the spin connectivity was completely mapped. And in fact, some German researchers took the lead from our group's published work, and they then looked at separating in the NMR spectrum mixtures of species with per deuterated species without resolved couplings, but yet being able to do a so-called spin chromatography with completely unresolved couplings. The corresponding COSY or relay, the standard experiment, is a mess. You do not really see the long-range ortho-para connectivity, which is so neatly showing up here. And there is a factor of between 2 and 4 sensitivity loss for the cross peaks in the traditional as compared to ours. We also worked a great deal with multiple quantum spectra. Much of this was done single-handedly by me in the early years. And this is the 2-dimensional double quantum spectrum called the inadequate, which came up from the lab of Ray Freeman. And you look for these pairs of peaks with the vertical axis being in the double quantum frequency and the horizontal axis being the single quantum frequency with respect to chemical shifts. 2 chemically shifted carbons were had a coupling, a J coupling, then you could excite the double quantum coherence. They would have a common double quantum evolution or nutation frequency or precession frequency. But when you reconverted them, because you cannot observe a double quantum directly, you have to convert it back to single quantum, and then you get the 2 chemical shifts. And the F2 dimension, the F1, you have the double quantum frequency. Now look at this in our hands. For the same per deuterated pyridine, no resolved coupling, but here is my spectrum. You have these pairs of lines as before, but you now have 3 additional peaks along the so-called pseudo-diagonal, which has a slope of 2:1. Not 1:1, but 2:1. Because the y-axis is a double quantum, the precession frequency is double the single quantum frequency in the x-axis. So if I make a pseudo-diagonal with a 2:1 kind of a slope, then you see I get for the spin 1 nuclei, not only the traditional double quantum peaks which you saw in the C13 in the previous slide, but you now get diagonal peaks on the pseudo-diagonal, which are 1 spin double quantum peaks. Because your deuterium, you got spin 1, you can make a double quantum transition in solution state from the Mi is equal to +1 state all the way to the Mi is equal to -1 state. The normal transitions are Mi is equal to +1 to Mi is equal to 0, and Mi is equal to 0 to Mi is equal to -1. But here you have the double quantum between Mi +1 and -1, provided there is a scalar coupling in solution state to a second deuterium. It's completely unresolved, but there should be a coupling. Provided that is there, we can excite and detect indirectly after reconversion to single quantum, the 1 spin and the 2 spin. So you have, this again was picked up by a German group. You have they had missed out the 1 spin double quantum altogether, by the way. And we were the first to show that for spin 1, you cannot just run the inadequate and say, okay, I got the same spectrum as before for C13. You do have the spectrum as before. There's 2 spin double quantum coherence. Like 2 carbons, you have 2 deuterons. But now you have a 1 spin double quantum, all of this with no resolved couplings, but non-zero couplings. What's more, with the same German group, we spent some time And with their hardware, we were able to show that a one spin double quantum spectrum allows you to amplify by a factor of 4 the J coupling, because the single spin, the single quantum J coupling in the multiplet will have a splitting of J hertz. The double quantum should have a multiplet of 2J splitting, but then the central line in the triplet of the spin 1 double quantum will be missing. And therefore, you have two lines with respect to the center. They're at plus or minus 2J. The splitting is 4J. So it is like you've amplified J by factor of 4. Incidentally, that's exactly what is going on in the rotating frame experiments also. European groups, to begin with, were somewhat skeptical when I pointed out that J coupling scaled up. They said, yeah, maybe it's not scaled down. They were right for the two spin half system. But for anything other than the two spin half system, 3 or 4 or more spin half systems, or 2 or more spin 1 or what have you, you really scale up the J coupling in rotating frame experiments, because those are strongly coupled zero quantum transitions. And here you have weakly coupled, unresolved double quantum transitions. For the one spin, they get a factor of 4 at unspin J. And the spin-spin relaxation time, okay, is 5/3 times for the double quantum one spin transition as compared to the normal single quantum transition. So what I'm saying is, if you had 3 seconds for the spin-spin relaxation time T2 for the single quantum transition, the corresponding single spin double quantum transition would have a T2 of 5 seconds. Or T2 is increased by factor 5/3. So the overall resolution enhancement, the J is enhanced by factor of 4 effectively, and the resolution, the line width is reduced by to 3/5. So the overall resolution factor is like 6.67. So it is not about just showing the connectivity and the coherence transfer in the rotating frame or in a multiple quantum spectrum of unresolved couplings. It is about amplifying these unresolved couplings and actually measuring them. And you see, we could then use it with this German group who were organolithium specialists, organolithium chemistry specialists, and we could actually measure the size of organolithium clusters in solution state by the methods that I had developed of one spin double quantum spectroscopy. I also went ahead and did triple quantum spectrum for Purdue-rated species with unresolved couplings. You get rectangular patterns of peaks, which are 2 spin 3 quantum peaks, and you also have 3 spin 3 quantum peaks, but I will not say more about that now. We did some work with the German group in plastic crystalline solids, where unresolved chemical shifts of deuterium in the exo and endo positions of camphor or norcamphor could be resolved thanks to a double quantum amplification of the chemical shift difference by factor of 2 in the virtual dimension F1 of the so-called quad shift experiment, which I came up with in those years with the German group. So you have essentially the magic angle spinning, which splits the quadrupolar coupling into a set of side bands, but then there is no information essentially other than the double quantum chemical shift in F1, and the chemical shift is now spread out by a factor of 2. So completely unresolved chemical shift differences between the exo and the endo deuterons. It's like 0.2 ppm here and 0.5 ppm here for the double quantum chemical shift. So it's like 0.1 and 0.25 respectively for the single quantum chemical shift. That is how well you can measure them apart in the quad shift experiment. Okay, we did considerably more work with rare spin 2D COSY with optimal sensitivity. This is the start of our optimal sensitivity experiments, which we came up with. We went beyond the unity bound that Sorensen had come up with, where he improved the sensitivity of inadequate by a factor of just a little over 2. But then we improved that by going beyond the unitary bound, by recognizing that some mileage is to be had by optimizing the relaxation pathway. Instead of letting the double quantum coherences evolve during the little t1, we would convert it using the double quantum sandwich as a filter, immediately convert it to single transitions of single quantum and let that evolve. And the single transition, single quantum relaxation rate is smaller than the double quantum relaxation rate. So we were able to go beyond the unitary bound. Typically, we get about 40% extra sensitivity by our methods, which we call as classy. Carbon, low abundance, single transition correlation spectroscopy. For carbon, we call it class C. For other nuclei like silicon and tin and so on, which Christy George pushed forward with, we call it LASI. Okay, and this gives us typically about 40% improved sensitivity in a given measurement time, which means equal sensitivity as the best experiment of Sorensen called the composite refocusing inadequate. This is not the traditional inadequate. This is already inadequate with a sensitivity improved by a factor of 2. And we are going further beyond that. 40% extra sensitivity or half the measurement time, going beyond the unitary bound. Okay, and that the reason is that whether you look at the extreme narrowing or the other extreme of spin diffusion, the relaxation rates of the various kinds of transitions always favor the single transition as compared to the double quantum. So get less magnetization losses or coherence losses if we do it our way. Use the double quantum as a filter, but the evolution is back to a single quantum, albeit with a single transition. And you see, this is how the ratio of the dipolar relaxation rate, this is never more than 0.75. The ratio of the single quantum relaxation rate to double quantum relaxation rate. Single quantum at best relaxes 75% as fast as the double quantum, and at worst, in spin diffusion, it can be, relaxing half as fast. Okay? And we have a lot of these spectra. I will not bother you with these. Here you see this kind of cozy spectrum with no diagonal. And this is our class C spectrum of sucrose, of menthol, of farnesol, of camphor, of silicon-29, of tin. I think George did something for tungsten, but she was not satisfied. She said, let me do this with this indirect detection. And we had some sequences in the literature. We improved on those with our approach. I will not bother you with the details. I think I should not test your patience. I'll just close within 5 minutes, if you will bear with me, please. And these are our sequences, again involving isotropic mixing. Please remember that our class C also involves isotropic mixing. So you see, Christy George used to make fun of me. Anything that anybody does in solution state NMR, you will want to completely come up with a different isotropic mixing version. Okay, so be it. If it works, why am I? Okay, so here is the high class version. Proton indirect detected. Proton indirect class C. We call it high class isotropic mixing. Look at the spectrum. We got some very unexpected results. Look at this. The F1 dimension now is the carbon double quantum, and the F2 detected dimension is the proton single quantum. And if you take alanine, for example, the CH3 proton should give you a doublet in the proton spectrum, right? Because it's coupling to the 3 methyl protons. Look at our experiment. We get one of the 2 doublet components with a sensitivity enhancement. So transition selectivity is propagating from the carbon-13 all the way to the protons in our indirect detection experiments. So you can see clearly, as compared to any other method in the literature, ours, whether with isotropic mixing or a somewhat watered down analog, we have much better sensitivity. Again, a factor of 2 improvement, reduced measurement time, or a 40% or still higher sensitivity enhancement. Okay, this can be used for 2-dimensional maps, more isotropic mixing with very high evolution frequencies. Look at these frequencies. In larger spin clusters, you can get 14 times the coupling constant, 7 times the coupling constant, 3 times the coupling constant in just a simple A2X2. You have 2 single quantum multiplets in A2X2, which are both triplets, with a spacing of j hertz between the triplet components. And here we can see 3j. And here's the example. Taurine in solution state, okay? And the isotropic mixing spectrum in the evolution dimension, 3j. 0 frequency and 3 times j, which is about 22 hertz. Here you have triplets with about 7 hertz coupling. So it becomes about 21 hertz in the in the 3J. In a gel, you have no resolution except the chemical shift. But in the same gel, our zealous experiment, which is a multiple quantum spin lock in the gel, gives you a neat measurement of 3 times J. And as I said, we can take this much farther. Okay, and we worked out the selection rules, what kind of composite spin quantum numbers will be active under isotropic mixing and so on, which goes well beyond our old isotropic mixing experiments. And Abhishek Banerjee went to town with diagonal suppressed experiments for abundant spins like proton. He also did it for, I had designed this experiment for in vivo work to work in the spin echo correlation mode, an experiment called SECSY, SECSY, not SEXY, SECSY. And I had worked it out for in vivo experiments. And Abhishek Banerjee, look at SECSY. You have all these quasi-diagonal peaks. The diagonal here comes up as a horizontal line. And the only cross peaks are here, and there are some cross peaks which are crowding near the pseudo-diagonal. But look at us. Dissect, volume localized, diagonal suppressed, spin echo correlation spectroscopy, not a single diagonal peak. And you can see the cross peaks, no matter how close they are to the pseudo-diagonal. Okay? That's what Abhishek was able to do in a volume localized mode. He also then went ahead to do it in ultra-fast mode, borrowing the technology of ultra-fast 2D NMR, which came up with Lucio Friedman, and using some of their web resources from Friedman and Giraudoux. Abhishek Banerjee in our group, we set up the ultra-fast dissect. Dissect is diagonal suppressed spin echo correlation spectrum. Look at any mixture, look at the kind of spectrum you get with the normal SECSY, and look at us. There's nothing here in the pseudo-diagonal, and very close-lying peaks can be measured. Okay, you can go on and on. I won't do that. He also came up with a high-resolution version of that. Abhishek was not happy just with the volume localized and with the low-resolution version of dissect. He then was able to come up with a very straightforward modification to make it the high-resolution version. And that works in high resolution. He also did it for exchange spectroscopy and in ultra-fast mode for exchange spectroscopy. And of course, Christy George did it for isotropic mixing with diagonal suppression in the 2D mode, and then the dynamic nuclear polarization of fluorine. Okay, where you have mixed scalar and dipolar interactions, you get huge enhancements, not only at X band, in this simple case by a factor of 20 when you have Oberhauser dynamic nuclear polarization, by adding a free radical and irradiating microwaves, but even at W band, you get reversed polarity because the dipolar interaction dominates at X band, while the scalar interaction of similar magnitude dominates over dipolar at W band. So you get about the same enhancement as it happens with very low power. Here we probably had about 25 milliwatts of power. Subsequently, we got about 200 milliwatts of power, and we got enhancement factors in excess of 1,000. And 2D spectra at X band for fluorine, Christy George worked out all of this, and the W band also. And at Q band, Abhishek Banerjee and Arnab Dey, just at 12 megahertz carbon, we can get 2D NMR 1,500-fold enhancement of carbon sensitivity as compared to natural carbon, the Oberhauser transfer ODNP. I will not give you the details. This is called a TODNP spectrum, transferred ODNP, where the electron spins of the radical polarize the protons, and then in turn they are used to polarize the carbon. So the overall gain in sensitivity in going from the Boltzmann carbon-13 at natural abundance to the transferred ODNP via the protons starting from the electrons is 1,500. You can do 2D at 12.5 megahertz. The fluorine 2D that I showed from Christie's work was 13.5 megahertz. This is 12.5 megahertz for carbon-13 Q band. Okay, I will not go through the MRI. I will just point out that we also came up with experiments with volume localized and volume localized 2D experiments here done in collaboration with the German group for a zero quantum volume localized 2D spectrum, which gives you clear identification and assignment possibilities of small metabolites, which are not available in the crowded normal 1D volume localized spectrum. We also did this with other two-way coherence transfer, indirect carbon detection and imaging. Here you can see selective imaging of the two components in a polymer blend. Here you can see the selective imaging of sucrose in a castor bean seedling during transport. All of this is our pulse sequence. The cyclic cross polarization was from a group of Kimmich in Ulm, and a pulse rotating frame transfer sequence with windows, which really makes it a very low specific absorption rate experiment from our group. We did some experiments with fuel cells with COVERY and with Professor A.K. Shukla, who was then director of COVERY, where we showed for the first time that proton electrolyte membrane fuel cell, the hydrogen oxygen fuel cell, can be monitored online by MRI. There's a lot of adventure here. I don't have the time to tell you that in this talk, but maybe some other time. You can actually see how the water is forming during this hydrogen oxygen reaction. Where is it accumulating? And if it is accumulating, the reverse reaction happens if you, or it will at least block the forward reaction if you don't give a voltage. So you can see what is going on, and in the flow field, water, which is the product of the reaction, is accumulating, we simply blow it off by adjusting the hydrogen and oxygen gas flow rates. And we can monitor this in real time in our lab. We also did some EPR imaging experiments way back in my CSAR, CRI years without any gradient hardware. And we had a gradient at the fringe of our electromagnet, constant over a 4 millimeter or 5 millimeter spatial range, which was about 450 to 600 Gauss per centimeter. And we could do some wonderful EPR images with that of chromium HMBA complex on leather. But our most recent work is dynamic nuclear polarized imaging. This is a 3-tube phantom imaged by NMR. Tube number 1 has no radical, but has the highest concentration of water. Tube number 3 and 2 have radicals, but 3 has the lowest concentration of water. And this is the EPR imaging. You don't see the tube which had no radical. The line width is between 4 to 5 Gauss, or at least 3.5 to 4 Gauss. And so you have to use a 40 Gauss per centimeter gradient. Here you use 1 or 2 Gauss per centimeter gradient. And you see with the OD and P, the tube number 1, which had no radical, is not seen. And the enhanced images are seen for the tubes number 2 and 3, where 2 had less water, 3 had more water. Most of it was D2O, but both of them had radicals. The NMR image shows all the 3 tubes without the radical or with the radical. Maximum water and minimum water, number 1 and number 3. The EPR image doesn't show 1. The DNP image doesn't show tube number 1. But then you see the enhancement of the quality. By far, the best sensitivity and resolution with our Overhauser DNP imaging as compared to either ESR imaging with these broad EPR lines or micro imaging with standard NMR. Just conclude this by saying there is a future. Instrumentation technology for MRI and for NMR involves cryomagnet, resistive magnet, permanent magnet technology, gradient technology, radio frequency technology, digital signal processing, image processing, computer technology, and software, of course. And then MR techniques, stochastic or Hadamard excitation. Stochastic excitation is something like Tsisov from the Berlin has been talking about for ages, for more than 35 years. And his Privatdozent and subsequently professor at RWTH, Bernhard Blumich, has taken it further. Stochastic excitation, and Freeman's group in particular for Hadamard excitation. These are low power excitations for MRI, be it by NMR or by ESR. And efficient wide line excitation by Wurst sequences at the hands of some of the former co-workers of Friedman. I think Shurko is the name, from Canada and now in the United States. But now comes the important thing, very exciting. Towards single spin detection, number 1, you can say, all right, you can lower the concentration detection of threshold of detectability. Concentration threshold of detectability, you can constantly lower it by one method or the other. Transfer from electrons or from abundant high gamma nuclei or other kinds of coherence transfer experiments. But of course, if you go to higher and higher magnetic fields, barring certain counter effects in relaxation rates, you might expect better sensitivity. And then the high TC superconductors might perhaps let you go to higher and higher fields if the critical field goes higher and also the critical temperature. But then the real interesting thing came up in 1994 at the hands of an orthopedist in the United States. This is a guy called Seidels, and he talked about magnetic resonance force microscopy. Let's not worry about the details of this. There's by far no time to talk about it. But in fact, Seidels, in his first paper published in around 1994 in Physical Review Letters, talks about a folded Stern-Gerlach experiment, where the physical spatial trajectory in the Stern-Gerlach experiment that the atomic beam took is folded back into the phase trajectory of an oscillator. So you have a cantilever on which your sample is mounted in a field with a huge gradient, 2000 Tesla per centimeter. Ladies and gentlemen, that is about, what to say, about 200 times what Stern and Gerlach had. They had, if I remember, 10 Tesla per centimeter, right? So these guys have 200 times that, 2 Gauss per nanometer gradient, sample mounted on a cantilever. It's a E prime center in a supracell W2 obtained by gamma irradiation, 10 to the 13 or 10 to the 14 spins per centimeter cube, and at IBM labs at the hands of Rugar, who had been a co-worker of Seidels and Iannone to begin with, independently published in Nature in 2004, a single electron spin detection by magnetic resonance force microscopy. What are the forces that they are detecting? They are detecting a force of the order of a few attonewtons with a 25 nanometer spatial resolution in a 1000 Gauss field. That has not yet extended, as far as I know, to single nuclear spin detection. As far as I'm aware, it stays with the single electron spin detection. Okay. And there are fears that there might be chaos, physical chaos, okay, not our mental chaos necessarily, but the physical phenomenon of chaos under conditions of strong coupling between the sample magnetization, or the force from the nuclear or electron spins of the sample, and the cantilever mechanical resonance. Because of that strong coupling there, one might have chaos, and if one enters into the chaos domain, that's a matter of a lot of further future research. Finally, I quote Goudsmit. Goudsmit said, then I want to say one more thing. Even if you make a minor contribution, even if it is not important, maybe it still gives you an enormous satisfaction because it's your baby. You dreamed it up and you got it going. You gave birth to the baby. Therefore, Goudsmit says, I do believe that one should not always necessarily aspire to tackle what is most important, but try to have fun. Working in physics, he said, but I would say working in science and obtain results. Now, I'm fond of saying a humble level of science that I try and do. There are different types of problems. People talk about, simple systems attack complex problems associated with simple systems. Or you talk about complex systems and you attack simple problems associated with complex systems. Well, I'm one of these naive guys. All my life, I've been a naive guy. All I've ever aspired to do is to attack simple problems of simple systems. And even there, I have made heavy weather, right? As you've seen. Thank you very much for your patience. Those guys whom I named already, the acknowledgements here, peace-wise. Thanks so much.